Okay, so in this question we just have to integrate this particular expression, but integrating will take a lot of time in this case because we will have to use 2-3 different types of substitutions in this particular question. So to begin with, you should observe first thing that everything in the denominator is of degree 4, right? So we have already seen one very standard case that when the degree of each term in the denominator is 2 and the values are sine and cos, then the process is to divide by cos square in numerator and denominator, or multiply by sec square in numerator and denominator, right? Since here the power is 4, we will multiply and divide by sec to the power 4x in numerator and denominator, right? So let us see what happens after that. So if I multiply sec to the power 4x in numerator and in denominator, I will get here tan to the power 4x, second term will become tan square x, and third term will become 1. So this is a much better expression, right? Now one more substitution will help me in converting this trigonometric expression into algebraic expression, which will be easier to solve. Okay, so look at this thing very carefully. I am substituting tan x is equal to t. If I substitute tan x equal to t, I will get, on differentiating both sides, I will get sec square x dx is equal to dt. This will happen if I substitute tan x equal to t. So I already have sec to the power 4. Let us give 2 secs to the dx value, so which on combining will be converted to dt. And what will happen to the remaining sec square value? The remaining sec square value can be written as 1 plus tan square, and 1 plus tan square is nothing but 1 plus t square, right? So your numerator will now become 1 plus t square into dt. And what about the denominator? Denominator is very clear. Since tan x is equal to t, your denominator will become t to the power 4 plus t square plus 1, right? So now again, when you see this expression, there is another standard form which you should remember. In this case, what we do is we first of all divide the complete expression by t square in numerator and denominator. Let us see how is that helping us. If I divide the numerator by t square, I will get 1 plus 1 upon t square. And when I divide denominator by t square, I will get t square plus 1 upon t square plus 1. I have swapped few terms, so take care of that. Okay, so this is what we have. Now again in this step, if I use one more substitution, that let t plus 1 by t, or it totally depends on the question. So here t minus 1 by t is helping us. If t minus 1 by t is, let us say, equal to u, then on differentiating this value, what do I get? I get 1 plus 1 upon t square dt. This value should be equal to du. Now this value on the LHS is very good value because this is the complete numerator of our integral, right? So if I use this kind of substitution, everything in terms of u will be written as integral du and nothing else. Everything is equal to du. And denominator, first of all, you need to see that 1 t square plus 1 upon t square plus 1 upon t square can be written as t minus 1 upon t whole square, but then we are getting minus 2 extra, so let us add 2 also, right? So this is the value of t square plus 1 upon t square, but t minus 1 by t is nothing but u. So basically in terms of u, t square plus 1 by t square is u square plus 2. But we also have one extra 1 here. So overall your denominator looks like u square plus 3. Now this is a very easy integral. Du upon u square plus 3 is what? In terms of tan inverse, 1 upon root 3. Tan inverse of u by root 3. This is our answer, but our answer should be in terms of x and not in terms of u. So let us substitute u. So you will be substituted as t minus 1 by t, but still that is not x. So then we will substitute tan x in terms of t, which will give us our final answer. Okay, so something like this will happen. Our answer right now is 1 by root 3 tan inverse of u upon root 3. Then when I substitute back value of u, it will become tan inverse of t minus 1 upon t upon root 3. And then when I further substitute value of t as tan x, I will get tan x minus 1 upon tan x upon root 3, which can be written as 1 by root 3 tan inverse of tan square x minus 1 upon root 3 tan x. And since we are doing indefinite integration, in every step you can just add some arbitrary constant. So if you add arbitrary constants everywhere, your arbitrary constant will reflect in the last step also. This is the final integral.